Welcome to the Early Career Professionals in Mapping webinar series. The American Geosciences Institute has partnered with the National Cooperative Geologic Mapping Program to highlight the work of early career geoscience professionals, especially as it relates to the use and production of geologic maps. Each webinar will begin with a presentation from an early career geoscience professional, followed by an interview. We are excited to introduce Nolan Dellerman. Nolan earned his master's in geology from the McKay School of Earth Sciences and Engineering. He works for Cyrq Energy and will speak about various projects, including the use of geologic maps to help locate geothermal energy sources.
Hi, my name is Nolan Dellerman, and I'm a geologist with Cyrq Energy. Today I'll be talking about the application of geologic mapping in geothermal energy. I'll start off with a brief introduction to myself, my background as a geologist, and my career path to now. From there I'll move into an introduction to geothermal, or Geothermal 101, including what geothermal energy is, how it's utilized, and some of the benefits. From there I'll move into geoscience in the geothermal industry, and talk about the basics geoscientific principles of geothermal. From there, we'll move into more detailed methods and examples, focusing on geologic mapping, as that's the main topic of this webinar, so I'll spend the most time and detail on that topic. However, I'll touch on other methods and examples from my experience as well, including types of data we collect and how it's interpreted, but I'll use geologic mapping as a basis for all of it, bringing it full circle to show just how important it is in what we do. From there, I'll showcase the final product of a geothermal project, including a detailed geologic map and a 3D model which was constructed on the basis of that map. Finally, we'll wrap up with the outcomes of what this work leads to, how geologic mapping can be a basis to successful geothermal well drilling and putting clean energy on the grid. A brief introduction to myself. I grew up in Northern Nevada and I'm a first-generation college graduate. I completed my bachelor's degree in geology at the University of Nevada, Reno in 2016. I became interested in the subject mostly for wanting to work outside. My professional experience as a geologist began in geophysical surveying and random field work during summers in college. I spent 2 years after my undergrad working as a hydrogeologist in mining. Following this, I went back to graduate school to get my master's degree in geology at the University of Nevada, Reno, where I finished up in 2021. My thesis for my master's was focused on geothermal exploration with an emphasis on detailed geologic mapping. I was introduced to this subject while working in a fellowship with the USGS Cascade Volcano Observatory. I had the privilege of being part of a field campaign in Yellowstone National Park, which was aimed at studying the fluctuations in the hydrothermal system using gravity data. Following grad school, I've worked in mineral exploration a bit before landing the job I have now with Cyrq Energy working in geothermal. When I'm not being a geologist, I like to do many of the things that outdoor enthusiasts in Nevada do, such as skiing and snowboarding, riding dirt bikes in the desert, and more importantly, hanging out with my family at all of the amazing things we can do in Northern Nevada. Now that you know a little bit more about me and where I work, let's talk about the industry that I work in, the geothermal industry. Let's break down the word. Geo means earth and thermal means heat. So geothermal is simply the heat that's been radiating from the earth for its entire history. The geothermal industry, therefore, is the multifaceted utilization of that heat available to us within the earth. I like to break this into two separate categories. The first category being geothermal direct use. Examples of direct use include heat pumps for homes, which use the insulating properties of soils as an underground radiator. Things like hot springs that are used for soaking and spas. This is by far the oldest category. And then district heating systems, which use relatively low temperature thermal groundwater to heat infrastructure. The other category is geothermal power production, which is shown in this cartoon by these diagrams in the center. Geothermal power production utilizes high temperature hydrothermal resources for production of electricity. High temperature means generally greater than 100 degrees Celsius. The other category of geothermal power production that we won't really touch on is called enhanced geothermal, which is depicted here. I work in the hydrothermal category, which is shown here, which is sometimes referred to as conventional geothermal, where we use geothermal energy to generate electricity from the grid, utilizing naturally occurring convecting hydrothermal resources. So how did geothermal systems form in the first place? This is where geoscience comes into play, where as geoscientists we try to figure out the mechanisms behind these resources and how they form. We know there's three main ingredients for geothermal resources to occur. The first ingredient is heat, which we know is readily available within the earth. The second ingredient is fluid, which in this case is just a vessel for the heat. And then the third ingredient is permeability, which is a fancy word for the ability of fluid to flow within the earth. The most difficult ingredient to source here is definitely permeability. And this is because in general, heat and fluid are pretty much everywhere, although in different quantities and distributions. But permeable pathways or fractures able to mine the heat and deliver it to depths that are economic for us to drill are really difficult to find at times. So the drivers behind this are ultimately plate tectonics, and this figure on the right sums up some of the plate tectonic settings we know about. Things like passive margins or mid-ocean ridges where things are spreading apart, or subduction zones where plates are being thrust under other plates, or collision zones where crust is being jammed into one another to form mountains like the Himalayas. But I want you guys to notice this side of the figure where things are pulling apart or where things get a little more interesting for geothermal. That's because when crust spreads apart, it gets thinned, and then many faults and fractures form as well. Specifically rift basins where, again, there's spreading going on, thinning of the crust so heat can come closer to the surface, and faults and fractures are forming to create these permeable pathways. It's really summed up eloquently in this quote here, where everything in geology can be explained by the Earth desperately trying to cool off and gravity relentlessly pulling everything down. It's interesting to understand that the plate tectonic mechanisms behind everything are really the driving force behind how these systems form and really how everything in geology can be explained. I spent the majority of my career both in academics and as a professional in the Basin and Range tectonic province. The tectonic province is shown in this black outline on the map. The Basin and Range can be thought of as a rift basin, although in area a little more dispersed and within the continent, which is a little bit unique. However, the mechanism is the same. The crust is extending here or pulling apart, and because of that, it's becoming thinner. With thinner crust means heat is closer to the surface, and also to accommodate the extension, many faults and fractures are forming. We discussed the three ingredients for geothermal to occur. These three ingredients are readily available within the Basin and Range, as exemplified by this map from SMU, which is a heat flow map for the US. You can see that the highest heat flow generally occurs coincident with the basin outline of the Basin and Range tectonic province. This is because, as said before, the crust is pulling apart here, so heat is shallower, and that heat is allowed to be mined to the surface via these faults and fractures. Furthermore, the Great Basin hydrologic province also generally coincides with the outline of the Basin and Range, at least over the state of Nevada for the most part. The Great Basin is, as the name suggests, a basin where fluid does not drain to the ocean. As such, there is plenty of groundwater available as a vessel for the heat to be mined close to the surface. So we've established now how the Basin and Range, or the Great Basin specifically, is a world-class geothermal province due to the tectonic setting and the unique circumstances in which all three ingredients needed have come together. Let's discuss now a simple model for how these convecting hydrothermal resources come to be. The first step is that meteoric water infiltrates deep into the basins to become groundwater over long periods of time. The groundwater is then stored in complex aquifers related to different rock types and barriers. Heightened permeability due to the faults and fractures formed from extension allow for the heat to be mined via the fluid available in the groundwater systems. A convective heat cell is then formed within these permeable zones, which brings heat from the source, which is again just crustal thinning or the shallow heat from extension. And so this hot water is then brought through these faults and fractures and forms a convecting cell that we can then utilize for geothermal energy production. Okay, now that we've established what geothermal is, gone through Geothermal 101 to understand what the tectonic forces and geologic principles are behind geothermal systems, let's talk about specific methods and examples from my work and what we do to explore for geothermal systems. We'll start with reconnaissance and prospecting. Small scale, think zoomed out, utilizing public data, existing regional geologic maps to hone in on areas of interest. We begin forming hypotheses about the presence of a geothermal system, and finally we may make field visits to make initial observations. So what does this look like? Here is a demonstration I've put together that shows what a typical desktop study might look like for reconnaissance and prospecting for geothermal. Our area of interest is shown in red and is actually part of a geothermal lease sale that was given by the BLM in Nevada a few years back. The first thing we might look at is something like a regional geologic map to just understand what kind of units might be in the subsurface, which are usually exposed in the ranges, the colored units, and then also look at how the faulting patterns present themselves. And here we have many faults mapped and some faults that cut quaternary units, which is indicative of a geothermal system in Nevada. We'll continue to layer in publicly available data, different maps. We can see that this map, although it's lacking pretty colors, is much more detailed and gives us a lot of insight into the faulting of the area. We see many faults mapped into the basin where quaternary units are offset, and this gives us a good footing when planning fieldwork to confirm or deny different faults and how they're mapped. You'll start to see a pattern and an emphasis now, as the next data set we're going to layer in is the USGS Quaternary Fault Database. This is a compilation of many different sources that just shows quaternary faults generally located in an area. If we focus in on the green faults that are mapped along this basin front, or range front rather, of the system we're looking at, we can see that there's a pretty prominent step over in those green faults. Step overs and fault bends and things like this are favorable fault patterns for geothermal. So we start to form a hypothesis now. Zooming in, we can see that even the place we're looking at is called Hot Creek, so that's indicative of itself. But when we look at publicly available hot spring data, we see that there's numerous hot springs within Hot Creek, the hottest of which is all the way up to 180 degrees Fahrenheit. So from this simple desktop demonstration, we should be able to start forming a hypothesis now that there's a system here controlled by a fault step over, where hot springs are daylighting in the center of that fault step over. From this, we start to plan fieldwork, where we may go look at the hot springs themselves, measure their temperatures, and also kind of look at the fault patterns to see if we agree with the mapping and to see if there's anything other, if there's any other things indicative of geothermal systems. As discussed before, field visits are really important parts of reconnaissance and prospecting for geothermal. The desktop study that we just looked at required a field visit to confirm and deny some of the hypotheses that were formed. We can see that things like hot springs, describing the hot springs, measuring their temperature are important parts of the field work for geothermal prospecting. This hot spring here is the 180 degree Fahrenheit one that I showed on that desktop study. It turns out that that was correct, and I measured this to be about 176 degrees Fahrenheit. Other things that we may look at are, again, different trends in the geology, such as this north-northeast trending alteration that I photographed at that same prospect. And looking at this vantage point from the range, we can see that there's a pretty prominent fault step over that I identified that correlates with what we looked at in the desktop study. Other things that we may look at in the field are investigating infrastructure like transmission substations to run by other colleagues, and things like access, land issues, even things like biology, which may be issues in the future as well. So what's next after we've prospected an area and decided we want to pursue it for geothermal? This is the early exploration stage, where more observations are made, more data are collected. We may start geologic mapping at larger scales or zoomed in scales. We may take geochemical samples of the springs, hot springs, and deposits of interest if they're there. We may deploy low-risk methods like shallow temperature probing, and we'll continue to utilize publicly available data, regional geophysical data, for example, LiDAR, and old well data if they're available. Here are some pictures of some of those early exploration techniques. This is a nice example of a shallow temperature probing survey done in Utah. You can see that this is pretty low impact, and once this UTV drives off and the probe is pulled out of the ground, almost no disturbance is left behind. Other examples of early exploration techniques are sampling for geochemistry of hot springs and other geothermal deposits. A big part of early exploration in geothermal is geologic mapping. It is my opinion that geologic mapping is really the basis for all of the work we do in geothermal exploration. I'll step through some field photos now that demonstrate what kind of rocks we might look at and what kind of data we might collect when making geologic maps. Here are some photos of some reservoir rocks, potential reservoir rocks rather, that we may encounter in the subsurface of the geothermal systems. You can see that we'll stop and make detailed observations and collect data at each of these types of outcrops. This is a particularly interesting one. Other types of data we may collect are structural data, as demonstrated by this little fault surface here, where we may measure the orientation of different fault surfaces and how they may indicate the local stresses of the field. Here's me standing along one of these faults in question. You can see that some of the places we get to work are quite beautiful. As such, I think that the geologic mapping stage just so happens to be the most fun stage in geothermal exploration. So let's dive into geologic mapping and what it means to actually make a geologic map. Mapping is an exercise in observations. As geologists, we will literally hike around and observe every rock outcrop we can reasonably get to in an area and just describe what we see. So this is a demonstration of what we might do at a specific rock outcrop. The first thing we might notice in this photo is that this part of the outcrop looks specifically different than the rest. There's a conspicuous polished look to this part of the rock. Other things we might start to observe and describe are things like these grooves that show up. These are called slickensides. Some other aspects of this outcrop that stand out are these little ground out parts of the rock that all kind of occur in the same shape and orientation, where the bottom parts are kind of missing. And finally, we may look over here and see that this part of the outcrop looks very brittle and broken up, and is also a distinctly different color than the rest. All of these observations come together into an interpretation of what we see in the field. In this case, we were looking at a fault surface. This cartoon describes what we just described in that rock outcrop. On the slip surface of the fault, we see striations and slickensides. In the core of the fault, we see broken up and damaged rock. So what do we do with the descriptions and observations we just made? From the observations we make at each place we visit on the map, we can start to connect the dots. This is where interpretation really begins and geologic maps start to form. Geologic contacts can start to be drawn in. This is where two different rock types come into contact with one another at the surface. And then also things like faults are mapped. In the case of the outcrop that we just described together, this is the map form of that interpretation. Making a geologic map, the process that we just went through is completed over and over and over until the map area is mapped. So this is a zoomed out view of that same map and that same fault outcrop at a much different scale. You can start to see how laborious geologic mapping can actually be, where so many observations are needed to allow for the interpretation of surface geology over this entire map area. You can see that this part of the map area is 3 miles across, and many faults and geologic contacts were observed and interpreted across this area. Now that we have a fair understanding of how geologic mapping is conducted in the field, let's talk about some other methods that go hand in hand with the early stage of exploration, namely geophysics. The photo on the left shows some workers digging in electrodes for an MT survey, which measures the electrical resistivity of the rocks below. On the right is an aeromag survey utilizing a drone, which flies a magnetometer across the area to measure the magnetic susceptibility of the rocks. On this picture, we have a vibro-seis truck, which is the source of seismic waves for a seismic survey, where the waves are thumped into the ground and then picked up by geophone arrays that are installed on the surface. All of these geophysical methods aim to map the subsurface using different properties of the rocks below and aid us in understanding our interpretations of faults, formations, and the geology below the surface. More useful geophysical methods in geothermal exploration is called gravity surveying. You may think that gravity is the same everywhere on Earth, but relatively speaking, gravity can change very minutely based on the geology below. As such, gravity surveying takes a fancy instrument called a gravimeter and just measures the different gravity signatures along a grid over an area. We use these data to make maps that show the density differences in the rocks based on the gravity signatures. This is an example of one of those maps, where the red colors and pink colors are gravity highs relative to the blue colors and green colors, which are gravity lows. These indicate how dense the rocks are and ultimately how deep the rocks are below the surface. We can use these maps to inform our interpretation of the structural geology or the faulting of an area and use it as a way to check our interpretation of the geologic map. Once the bulk of the early exploration stage is complete, we should end up with something similar to this, a final geologic map which considers all of the data. This detailed geologic map is our basis of understanding for what should be going on in the subsurface. We'll take this map and draw cross-sections across it in a favorable orientation to where we will take our interpretation into 3 dimensions. On the following slides, I'll look at this cross-section here, which is C to C prime in this location, and show you how subsurface interpretations in 3 dimensions are starting to be formed. As mentioned, we'll start looking into subsurface mapping at this point, and this is contingent on if the results of early exploration are promising. In general, if there are indications of a good economic geothermal system, which we can start to delineate from the geophysics, the geologic map, and our understanding of the area. From here, initial 3D modeling based on the geologic map and the geophysics is carried out. As mentioned before, let's talk about cross-section C to C prime across this geologic map. This is a detailed version of that cross-section. Let's talk about how we got to this interpretation from the data we collected in the field. These interpretations, the orientations of faults, how thick bedding is not just conjecture, but is based on actual data. An example of this are things like angles of faults or dips of faults, and then angles or dips of bedding in the subsurface. These are measured in the field with a compass and then projected along the section into the subsurface to create a 3D interpretation. Things like the gravity are forward modeled along the sections to make sure that concealed features agree with where gravity is located and that the magnitude of these offsets also agree with what we know from the gravity. Once we're satisfied that our interpretation makes sense, agrees with all the data available, and in general is geologically reasonable, we'll move into simplification so that we can take this into 3D even further. It may seem counterintuitive to simplify the detailed geologic map, but a lot of these details simply don't translate into 3D easily, or will just make a file too big to use. So simplification is deliberate and usually is into major faults and major lithologic packages as so. Once the geologic map has been simplified in a reasonable fashion, we'll move into the subsurface to simplify the cross-sections as well. Units are generally grouped together by age. In this instance, Quaternary, Tertiary, and Mesozoic units were grouped. Major faults are also grouped and constrained, given an ID, and correlated across the field from section to section so that when modeling in 3D, we know which fault is which. In this case, they were color-coded. The following movie is a simple showcase of a 3D geologic model built using the workflow that I just described, of simplifying a detailed geologic map and cross-sections into a reasonable form where we can build the 3D geologic framework. In a geothermal project, once the early exploration is undertaken, a 3D geologic model has been established, we can move into a different phase, the appraisal phase. Here we may drill additional wells, like temperature gradient wells or core holes, to further constrain our understanding of the geology and the temperature in the subsurface. We'll continue to update our 3D model with new, deeper, better quality data, and will ultimately estimate a power generating capacity of the project. Shown here is a 3D view of the same model that we already looked at. However, it's now populated with additional data. The small black lines are actual wells that have been drilled in the past year with temperature data associated with them. The contour lines shown at the surface are very shallow temperatures that have been collected and modeled. Other things shown in this model are interpretations of the deeper subsurface temperature from that temperature that we collected in these wells. These are isosurfaces or contours in the 3 dimensions of modeled temperature from 275 Fahrenheit, which was encountered in this well here, all the way down to 350 degrees Fahrenheit, which has not been actually measured, but has been calculated from geochemistry. This type of model is used to both understand the power capacity based on the geologic framework and how it matches up with the subsurface temperature, as well as target new wells like this one here, which aims to encounter the deep temperatures and ultimately the resource. If the results of exploration and appraisal are favorable, the project will likely then move to the development stage. Development of a geothermal project includes drilling of full-scale wells, well testing for power plant design, and likely the development of a reservoir model. A reservoir model is a numerical simulator that's used to forecast how the field will produce over the lifespan of the project. Let's talk about some of the positive outcomes that can come from geologic mapping and geoscience in general, at least in the geothermal industry. Shown here is a well that was drilled based on the geologic modeling techniques that we discussed in this talk. This particular well produces enough power for 2,000 residential homes per year. There's some other benefits to being a geoscientist in geothermal, which is some of the really cool things you get to see in well testing phases and in drilling. Shown in this quick video is a well test being conducted where water is coming out of the ground and ultimately boiling in the sump.
Boiling.
Finally, I'd like to thank the American Geosciences Institute for putting this webinar together. I'm passionate about geologic mapping, and I hope this was an informative talk to showcase how geologic mapping is used for different parts of different industries. I'll leave you now with a quick thread of wisdom from the field before we move into a Q&A.
As geologists, it's really important that you take note of what kind of rock we have snacks on, because it's an important scientific observation. You know, one mythology snacks a little better than the other. It's something that has to go in the report.
Hi, Nolan. Thank you so much for sharing some of the work that you do related to geothermal energy. Lindsay and I are excited to dive into some of the details and hear about your experiences leading you into this stage of your career. And just a reminder for the audience, if you are tuning in to the premiere, Nolan is available to answer questions in the chat. So Nolan, I thought we'd start off by talking about your video at the end of your presentation where you're discussing making observations of rocks where you should eat your snacks. Can you tell us some more about your snacking experiences and recording that video?
Sure. So that video was sort of an off-the-cuff recording I took after a long day in the field, a long week in the field, where I remember looking for a rock outcrop to sit down on about 2 in the afternoon. It was hot out, thirsty, hungry. And I remember taking like 10 or so minutes to find the right outcrop to have a seat and eat my snack. And I remember thinking, wow, this is a scientific, driven thing of I'm looking for the perfect outcrop because certain outcrops are jagged or sharp or uncomfortable to sit on. And I remember, making that observation going, I really was deliberate and scientific about what outcrop I chose to sit down and eat my snack and be the most comfortable and the most happy. So that's kind of where that came from. And I remember thinking, I should capture this observation. And now I'm glad it got to see the light of day and to share that kind of silliness of what goes on in the field, especially when you're alone in the field. You get a little bit kind of loopy and you're in your own head and you're kind of funny. So that's where that came from, and hopefully that lands with some of the people.
You should make an app for others who do field work so that you can share those spots.
Yeah. I'll start making GPS locations of the best snack spots, and we'll make a chart and share them around.
That's great. So you mentioned in your talk also that you pursued a general master's in geology. So what made you pursue that degree in particular as opposed to something more specific?
Yeah, so when I decided to go back to graduate school, I did know what I wanted to do, and I did know I wanted to go into geothermal. So me pursuing a more general geology master's was just so that I could have a better overview of geology in my master's degree and not get fully kind of pigeonholed into the one thing. Although my research and my master's thesis was specific towards geothermal exploration. But I think one of the underpinning things there is that geothermal is pretty multidisciplinary. So during my master's work, I was able to collect geophysical data and interpret it. I was able to do geologic mapping. I was able to do a number of things, dealing with temperature in the subsurface, dealing with, hydrology. And so it was kind of an all-encompassing master's degree, but with an emphasis on geothermal at the end of it. So hopefully that answers the question, but I think it was more so to just get an overview of how we can use geoscience and geothermal, which is, again, multidisciplinary.
Thanks. And then related to that, so you got a master's and then you went into geothermal. Is that required for your position to have a master's? Can you do it with a bachelor's? Do you need a PhD? And then also, like, how did the training go for your job related to your schooling?
Sure, that's an interesting question for the geothermal industry, which is still, it's not new, but it's still kind of niche and a little bit small. So I would say that it's not necessarily required that you have a master's degree, but it certainly is favorable and helps your odds of getting a job in this industry, which is small and a little bit competitive. I think a lot of geoscientists are wanting to get into renewable energy and also oil and gas geologists are wanting to leave that industry to come to geothermal because there's some tie-ins and similarities. So I work with geologists in geothermal that have bachelor's degrees, and then I've worked with geologists that have PhDs and everything in between. So I think it's more so just understanding how you can use your degree to get to where you want to get in certain industries. And so if you get a master's degree and you're deliberate about it, I think it'll help you in your path in a certain industry, geothermal in particular. And then the second part of the question, take a pause.
So the training. So you had your master's degree. How well did that prepare you for your position? Did you have to get on? Did your company provide training for you? What did that look like? Did you have a mentor that kind of walked you through it? Just again, the process of figuring out what you were doing in your job.
Yeah, so the training part's been a little bit kind of touch and go for me in terms of on the job training. I did learn a lot about exploration techniques in my master's degree, which helped me a lot in my job now. Some of the mentorship that I have gotten have been from colleagues more so than superiors, meaning, I work a lot with engineers, reservoir engineers, to do numerical modeling and to do well work in our power plants and well fields. So I've learned a lot on the job from them about well testing and some of the more quantitative engineering type work we do. In terms of actual mentorship directly for the geology side, I haven't gotten a lot of that where I'm at. But there's a lot of opportunity for workshops that I've participated in that my companies help sponsor, and just going to conferences, professional conferences, and listening to talks and reading papers and this type of stuff to just stay up to date with what people are doing and apply techniques that people are publishing to the work we do at Cyrq and these types of things. And then in terms of specific training for like software we use, the software package that I use for 3D modeling is called Leapfrog, and that's run by a company called Sequent, and they have really good communication, and they offer training to understand how to use that software package. So I've utilized that, and they've been really great. So it's just kind of finding your way to piece it together in terms of training. I think the industry I'm in is, again, really niche, and so there's not a lot of widespread training opportunities for geothermal geology. You kind of have to figure it out as you go, which is part of the fun of it at the end of the day. So.
That's awesome. And it's funny you mentioned Sequent. They're one of our newer Earth Science Week partners, and they just made a model. They're doing 3D modeling for teachers and students that can play around with it. So it's a great tie-in and a way to kind of model your work for teachers and educators and students. But I did want to ask. Oh, go ahead.
I was just going to say Sequent, yeah, they're really great. They have a team of geologists and really, really good, top-notch scientists that are putting that software together, and they're also doing the learning part and the training part for people like me, and they're making the tools like you just mentioned for for education, and so it's a really great thing. And they're a big company with outreach to all different industries, including mine in geothermal. So really cool.
And then you mentioned the reservoir engineers that you work with. Can you talk about other types of collaborators? I know that geology and geoscience in general, it's not just a one-stop shop. You work really closely with other professionals. Can you talk about some of the different types of professionals and careers that you work with?
Yeah, so yeah, for sure. So the engineering side is one, and so reservoir engineers are kind of a mix between an engineer that you would think of and then a geologist. They have a lot of geologic training as well because they're dealing with the subsurface. So those are the people I work the most closely with in geothermal, and we work together to try to understand the subsurface at our geothermal projects and how things are moving and how we can forecast and simulate with numerical modeling how those things will act in the future with certain scenarios of producing fluid from over there versus over there, and how that might affect things and make more power at the end of the day. Some of the other people that I work with on a daily basis are more classic engineers like mechanical engineers and electrical engineers who work more on the power plant and the surface side of things. And so, right, so we have sort of a subsurface discipline that work together and a surface discipline that works together. And, we take things from the subsurface and bring them to the surface to make power. So we have to work closely together to understand, what's going on their end, and they need to understand what's going on our end. And so there's a lot of cross pollination, call it, of engineers working on the power plants, understanding what's going on the subsurface from us and vice versa. Some of the other professionals I work with are more, earth science focused people, geochemists. Geochemistry is a really big part of geothermal, and I'm not a geochemist, so I'm trying to learn. And ultimately, we have to rely on consultants sometimes that are geochemists to collect data and interpret data for us, and then also the geophysical side. So I work very closely with geophysical, data collection companies or vendors that will go out and do the surveys for us, and I'll oversee that and collaborate with them on survey design. And then we also work with geophysical modelers, and those are the people that kind of process the data for us and give us a final product that we as geologists can understand and interpret. So there's a lot of go between different disciplines of earth science and geoscience that goes on. And then lastly, there's a lot of collaboration in this company. We work very closely with like the finance group and this type of thing to understand the economics of the projects that we're working on. And if we want to drill a well, right, we have to work very closely with that side of the business to understand, okay, how can we make sure that this is going to pay off in a reasonable amount of time, and not just spend all of our dollars doing something that doesn't benefit in that regard. So this is something that I've learned very quickly on the job of how to think financially and economically, and try to think of how things will actually pay off, because at the end of the day, we are a business that is trying to make money, and that's a part of the business that scientists often don't think about, especially coming up through school, but is a very important part. So
Yeah, it sounds like an important skill to have.
yeah.
And speaking of going back to talking about the computer software you were talking about, did you foresee yourself being in a career where you use computer programs so much? And is that something that you've really learned on the job and that you recommend people coming into the field are more aware of?
Yeah, that's a great one, because, when I was first getting into geology in my undergraduate, I really didn't foresee myself using a lot of computer software. I was really field focused and felt I was strongest as a field geologist. And frankly, I still feel that way. I consider myself a field geologist still, but using the computer software is something that in this day and age, you really can't get away from as a geologist. I mean, even just things like the mapping software, just GIS software is something that's ingrained in geoscience education, I think, across the board. So that's one software that I was familiar with from the very beginning. But the 3D modeling software, the Leapfrog software from Sequent, is something that I did learn on the job, again, with help from them and their training courses, and just learning it kind of through trial and error and figuring things out as I go. And that's not something that I ever thought of myself as a 3D modeler, but I have taken it on pretty quickly and learned it, and it's fun to be able to understand how it's useful and learn how you can apply it. And so I didn't foresee myself doing that, but I'm glad that I'm going that route, and it just broadens my horizons as a geologist to really go from the field and looking at rocks and making observations all the way through to the modeling side of things. And so it's kind of, I would say, it's satisfying to go from like collecting rocks and making observations in the field to all the way to something that's comprehensive like a 3D model. It's kind of from beginning to end. So I would encourage people who are studying geology to not be shy about, because a lot of people are just focusing on the computer side and the programming side. And I encourage those folks as well to be open to going in the field and checking that side of things out, and really kind of broadening your brush to understand how each piece fits together and what it all means in the end. So I'm glad I went that route. I didn't foresee it, but it's been pretty fun to learn.
That's awesome. You're just talking with some professionals last week about that are on the programming side. And it's like, yeah, it's nice to know how to program, but we don't know what the content is. And so having that experience of having the field work and the programming definitely is an attractive skill and trait. Awesome. And so most of your talk obviously is on geothermal energy, which we'll get to in a little bit. But before we dived into that, I wanted to ask you about your experience in mineral exploration. Can you talk more about your work and the different experiences you've had in that?
Yeah, sure. So I did mineral exploration work for almost 2 years, sort of starting when I was still finishing my master's degree until I found the job I have now in geothermal. And what I was doing was really in a consulting group for mineral exploration. So we were working all over Nevada and a little bit in Idaho as well for different smaller mining companies that were trying to bring their projects closer to mining, to actual mining stages. And so that was a pretty fun experience, and 95% of it was in the field. And so that video that I shared at the end of this presentation was from a mineral exploration job I was on, where we were up, collecting rock samples for geochemistry and doing a little bit of mapping. And that was actually for lithium, hard rock lithium exploration. And so that work was kind of all over the board. We did gold exploration, lithium exploration. I did everything from kind of reconnaissance scale mapping of basically whole mountain ranges over, weeks at a time to kind of look at where areas of interest might be and take samples in a very broad stroke of sampling, and then also really detailed stuff where projects were further along to map things at really fine scale and collect all sorts of soil samples and stream sediment samples for looking for gold anomalies, and all the way to, I was part of a drilling campaign as well. And it'd be great to show that picture of some of these little drilling rigs we use for mineral explorations. I did about a month or 6 weeks worth of drilling where we drilled like 40 different holes all over this mountainside, and sampling and describing the rocks as they're coming out, and working with the drillers. And it was a really fun experience and a lot of time away. So that was one of the drawbacks of that work. The mineral exploration work is it's, big chunks of time away and living out of RVs and hotels and camping here and there, which is a lot of fun. But I am a young professional, but at that time I was starting my family, and so being away from my wife and at the time, infant daughter was pretty challenging. And so moving into geothermal kept me a lot more at home, which is great. So I got a better work-life balance now. But the mineral exploration work was really fun, and I do miss it at times, just being out there, kind of Indiana Jones style, kind of prospecting and picking up rocks and mapping, and it was a great time. So
That probably speaks to a lot of people who want to get into geology. A lot of us picture that being out in the field and, like you said, Indiana Jonesing it. Yeah.
yeah. So I've always said this, but like the mineral exploration, at least from my perspective, is kind of like the sexiest thing in terms of geology. And so you're really out there kind of in an intrepid fashion, doing old school geology and mapping and collecting rocks, and you're out there. I even had like a Pulaski or like a pickaxe at one point, like digging out old prospect pits and like thinking about how 100 years ago people were prospecting the same areas. It was a really fun time, but it's definitely only for a certain type of person to do that as a long-term career, right? I mean, you're out there traveling all the time and potentially dangerous situations by yourself. I did a lot of solo kind of field work with no cell service, and that can be a little bit hairy. So those are the kinds of considerations if you're thinking about mineral exploration. It's a little old school, but a lot of fun. So
I'm really glad that you had those experiences, but we are very happy that you went into geothermal work because your presentation was an excellent breakdown of it. So as someone who doesn't know very much about like the ins and outs of geothermal, like you had a great explanation of the work that you do and what that accomplishes. So can you speak about how popular or prevalent geothermal energy is in homes or industry?
yeah, that's a great question. I think I alluded to how geothermal is still kind of new, even though it's been around for frankly 100 years. So the first geothermal was put together in Lardarello, Italy, about 100 years ago, very small scale. And since then, I mean, it's still been kind of piecemeal. It's a little difficult to figure out. And for a long time, and even to this day, electricity generation from geothermal is kind of focused on the tectonically active areas like, the Western US, places like New Zealand or Iceland. The East African Rift in Kenya is becoming a geothermal, hotspot. Forgive my pun. But, in general, geothermal is kind of niche still and small. And so being able to use geothermal across the globe is becoming a very popular new thing. And there's a couple of different ways that that can be achieved, right? So the classic geothermal, conventional or hydrothermal systems that I work in, again, are focused only where they exist, right? Where the resources, hydrothermal resources, are active. And so that's kind of like the Ring of Fire or tectonically active places. But other forms of geothermal are things like geothermal heat pumps, which I alluded to quickly in my presentation. But these are things that can be deployed anywhere, basically. And it's not a resource-based geothermal kind of source. It's just using the insulating properties of the soil beneath like a residence or a building to kind of use it like a radiator. And that can actually help as a heat pump to use as heating in the winter, but it can also help use to reduce costs and reduce energy load for cooling in the summer as well. Because, if you go a certain distance down into the earth, 6-8 feet down, it's kind of a constant temperature all year round. So you can utilize that as a radiator to help basically heat and cool and reduce electricity load and costs for your residence or for your building. And then the other thing that's becoming really popular and the technology is kind of beginning to take off, and there's lots of Department of Energy funding that are going towards research projects for what's called EGS or enhanced geothermal, which is essentially, hydraulic fracturing of the rock where there isn't a natural convecting resource, but there is heat. And so it's hot, dry rock or enhanced geothermal to go down and make our own systems, basically. And there's some projects that have recently been successful in proving that this is possible. And that is becoming kind of a geothermal anywhere initiative, understanding that it's not fully anywhere. I mean, you do still need to have enough heat close enough to the surface to drill into. But in general, if you go down into the subsurface, there is heat kind of everywhere. So, the conditions do need to be favorable for it still, but less favorable than they do for conventional or hydrothermal systems. And so geothermal is becoming much more prevalent. It is taking off, I think. There's obviously with the climate change that we're very concerned about across the globe and across governments. There's pushes towards renewable energy, and geothermal is one of the more favorable renewable energy sources because it is base load, right? If you think about solar and wind, that obviously solar is great, but it only works when the sun's shining, or wind, which is great, but only works when there's winds blowing. But geothermal, once it's developed and online, it's online all the time, 24/7. It's a base load resource, so it can fill a lot of those gaps where renewable energy is kind of swinging, day and night or weather dependent. Geothermal can kind of pick up the slack. So it's becoming much more important, and it's going to start growing, I think, exponentially as we have a push towards renewable energy even more. So that was a long-winded answer, but I'm passionate about geothermal, so I think it's pretty exciting, and we're moving towards new horizons in geothermal, I think. So
yeah, and I think it's interesting because when you showed that map where it did look like really the Western United States really was the only area that had the opportunity to use geothermal, I love that we're able to use it anywhere. I mean, you mentioned how it's kind of expanding into different types of energy versus just kind of digging down and using the heat deep in the earth.
yeah.
Can you talk just a little bit more about how do you determine which system you should go with, or that would be best for the area from an economic standpoint and just from a possibility standpoint?
Yeah, so I mean, you just kind of answered the question a little bit yourself there with it. It is, it's mostly driven by the economics of it, right? You have to understand. So that's part of one of my main jobs as a geothermal geologist for a developer, right? Is I basically am telling the financial people, the people that run our company, okay, this project is worth this many megawatts of electricity, right? Based on the analysis we do, the modeling we do, that we understand the temperature distribution, the permeability distribution, and we use analogs to say, okay, this system's a lot like this other system that's producing. We know how much energy per square kilometer. That's one common method we do, which is called a power density analysis, to understand, okay, if this system is X, Y, and Z kilometers of resource area at this temperature and this productivity, we know it's worth this many megawatts, and that many megawatts is worth this many dollars. So that makes it an attractive project. But it's not only that as a consideration. I mean, it depends on a lot of different factors, things like cultural impacts, right? I mean, a lot of the systems, especially in Nevada, are kind of right on top of small towns or are within Native American reservations or things of that nature, or have kind of culturally or historical significance with hot springs and things of this nature. And so these are major considerations as well, right? We don't want to develop a project that's going to, destroy cultural significance, and we want to make sure that we have a good working relationship with the public and the people that we work with in these areas. So that's another major consideration. And then also just the risk involved, the subsurface risk of how difficult and how risky is it to produce or to develop a project. So that's more of the scientific side, the geologic risk side, which is another major driver. So I think those three buckets are kind of the main ones for how we decide which projects are the best and which ones we go after. And so that's something that I've been working on lately for the company I work with, is to put together a package of these are all of our projects, and rank them based on all of these different risk scenarios. So I'm learning a little bit about statistics and probability now as well as a geologist. So it's, that this is again a full circle back to geothermal just being multidisciplinary and multifaceted, and you really have to kind of not pigeonhole yourself and be able to understand all these different things and work with different people. So hopefully that answers the question. I went off a little bit there on a tangent, but I think it's important to talk about all the different problems and risks and challenges we face in geothermal, because it is difficult to access these resources, and it is risky. So it comes down to the risk at the end of the day. So.
Yeah, so if I understand this correctly, and of course, correct me if I'm wrong, that the geophysical techniques and technologies that you use are really helping you assess some of those risks ahead of time, right? So we'd love to see more about like their outputs and like just more of those technologies that you use.
Yeah, so the geophysics are a really important piece of the puzzle, especially in areas where the geologic exposure is poor. There's not a lot we can do on the surface. We have to kind of use geophysics to be able to look into the subsurface and help us predict what we're going to encounter when we start drilling. So I can share a little picture of some geophysical data in 3D now. Okay. So this is a view of the 3D model that I used in the presentation, which was built mostly on geologic mapping and building cross sections. But we did collect a lot of geophysical data at this project as well. And so I showed a little bit about the gravity that we collected here in the presentation. So I'll talk about the MT, the magnetotelluric data we collected here a little bit. I'll show some of the outputs of that. So magnetotelluric data is an electromagnetic type of data set that's collected using kind of the natural electromagnetic kind of signature that's just natural to the Earth, using the magnetic I'm not a geophysicist, so bear with me, but using the magnetic field of the Earth and the natural sources of electromagnetic signature. And what you do is you put these electrodes in the ground and understand how that electromagnetic current goes through the subsurface. And then the product of that is the resistivity of the subsurface of the different rocks below. And so this is an example of what a magnetotelluric data set might look like after it's processed in 3 dimensions. And the different colors you're seeing are different resistivities. And this is a bit of a messy block model, but what I do as a geologist with these data is once they're processed and I get kind of resistivity values in 3 dimensions over this block model, is I'll kind of isolate different resistivity values. And so here's an example of that. So the orange blobs you're seeing here are resistivity values that have been modeled in the subsurface of this area that are less than 3 ohm meters. And that might be meaningless to most of you, and it kind of is to me a little bit. But in general, what that means is this is very conductive rock. And conductive rock in a geothermal system can mean many things. And the main thing that it means is that clays or hydrothermal clay deposition has a really conductive signature, meaning it conducts electricity, and this survey has recognized that these areas are highly conductive. And you'll see that the distribution is kind of funny right out here in this flat lying area in the far reaches of this basin. The conductivity comes all the way to the surface. And that can probably be explained by the playa out here. So playas also have a conductive signature. But when we zoom in a little bit and look at the conductive body that's in this area, we can start to make interpretations of what that conductivity means. And in this case, we're pretty certain, based on the temperature that's been measured and the interpretation of the geothermal system, that this is hydrothermal clay deposition from the outflow of the hot water into this basin. We can also isolate different parts of the resistivity signature. So deeper, we can look at this range of 30 to 60, which from people that have studied this for a long time in literature, we know that this resistivity range is potentially indicative of hydrothermal alteration mineral assemblages like propylitic alteration that occur at certain temperatures. And so we have this nice shape here in the subsurface of this 30 to 60 ohm meter kind of signature, right? That we've interpreted this to be correlative to where the upflow of this geothermal system is, where it's hotter and where it's altering these rocks and depositing those minerals that show that resistivity range of 30 to 60. So we can kind of put this picture together of the resistivity in the subsurface, where this kind of moderate range, indicates the hydrothermal mineral deposition where it's hotter, and as it comes up closer to the surface, it's cooling and eventually outflowing into this basin. The yellow is the alluvial sediments in the basin. And so it's depositing lower temperature clays into the basin. And so we use this to kind of put the picture together, alongside the geologic mapping and the geologic framework with the gravity data that helps us constrain where the faults are and how they're oriented. And so all of these things kind of come together in this puzzle to show how this system is working and how it's plumbed. And from there, we can start to plan where we want to drill, and we can start to reduce the risk because we have multiple lines of evidence and data sets that are pointing to the same interpretation. And so we can start to build our confidence that when we drill a well where we think there's hot fluids, that we're going to encounter them. Obviously, there's uncertainty with this, right? I mean, until we drill this blue blob, we don't actually know what it is. It could be something else, but based on all the other interpretations of the geology and what else we know about the subsurface, we have a pretty good idea of what it is, and that helps us reduce the risk before we start drilling.
That's awesome. And it's great to know the technology nowadays that professionals can do that more safely. And I think about even like 20, 30 years ago, people that were drilling, it's like what they were encountering and the lack of information they have compared to what you have now, especially with that manipulable model. It's awesome.
Yeah.
And so I know that we're probably running short on time here. So we're going to jump to our last question that we typically ask all of our early career professionals is, what is in the future for Nolan? Where do you want to go from here? And what does the future hold?
Yeah, so this is a hard question because I haven't thought about this a lot lately. I'm kind of where I want to be for now. And so I'm kind of cruising. I'm pretty happy, but I think my professional goals are to just continue to become a geothermal geologist, to become, an expert in my field. I think, geothermal is really becoming important, like I said. And so I'd like to be at the forefront of what's happening in geothermal. I'd like to be part of all the new technology and really kind of become a geothermal kind of expert. So that's my kind of broad goal, and what that looks like, I'm not sure. I'm happy working in the developing role I'm in now, working for an operator. But potentially my long-term goal, 20-year goal, call it, is to maybe go back and get a PhD and get back into the research side of geothermal as well. I'm certainly open to that. But I'm kind of just playing my cards however they fall right now, and enjoying my career as it is, and however that growth happens, I'd like to just kind of let it happen. That's a little bit of a cop out to your question, but I think my professional goals, like I said, I'm where I want to be, which is an interesting feeling. But I think just growth in the industry I'm in is my main professional goal. So
yeah, that's wonderful. And I think both Lindsay and I want to see that map of the best snack locations. That should be a goal in the future, is to get that established for hikers and for geologists.
That's a really great goal. I'll definitely add that to my list of goals.
Awesome. And Nolan, thank you so much for talking with Lindsay and me today, and sharing your work. We learned a lot about geothermal energy, and especially also how it relates to geologic mapping. So thank you again. And again, if you have any questions for Nolan, feel free to put them in the chat, or send us an email.
Awesome. Thanks for having me.
Thank you for attending today's webinar. If you have any questions that were not addressed today, please email them to us at webinars@americangeosciences.org with the subject line EC Webinar-Nolan Dellerman. Please join us for the next webinar in this series, which will feature Sydney Lance, who is from the Natural Resources Conservation Service and will talk about her work in soil mapping. To access the recording of today's webinar, as well as the rest of the webinars in this series, please visit the Early Career Professionals in Mapping YouTube channel.